All right, properties of waves. So we're mostly going to spend our time here doing transverse wave things, but I am going to take a minute to just tell you a little bit about longitudinal wave properties, right? So there's one major one, really, right? And so right here, we call this a compression. It's a compressional wave after all, right? So when you see that the spring is compressed or the air particles are densely packed together, that's a compression. And then this section where the slinky or the air particles are farther apart or less densely packed, that's called a rarefaction. Now, I'm never going to test you over whether you know that it's called a compression or a rarefaction. That's just terminology that we might use. I tend to use them when we talk about compressional waves just because it's in my head. So now it can be in yours. Okay. That's it on compressional waves, longitudinal waves. We're going to move on to transverse waves now. All right. Okay, so before we go on too much further, here's a longitudinal wave, right? And you'll notice this is the resting position, this green dotted line, okay? And the blue line is going to represent the actual wave itself. So what we've drawn right here is one wave pulse, okay? So imagine that you have, like a string or whatever that's going along, and then all of a sudden, right, you've got this wave pulse and it's moving along your medium or whatever, in your water, on your string, whatever, slinky, doesn't matter. So this wave, this is considered a pulse. That was funny. It's supposed to be an arrow. There we go. This is considered to be a pulse. Okay. Now, you can also have a periodic wave, which is something that's kind of oscillating. You're creating a wave that's the same over and over and over and over again. This is a periodic wave because it's happening periodically. It's happening over a period of time, right? All of those things there's a reason for that, right? So it's called a periodic wave. All right, cool. So let's draw a periodic wave and then we'll talk about it. All right. So here I've got a periodic wave drawn. Okay. And so this is a type of longitudinal wave. And if you could with me imagine that all of this is symmetrical, that it all looks the same. Okay. It turns out it's actually very, very hard to draw a perfect repeating periodic wave over and over and over and over again. I kind of made tiny little mistakes, but it's probably close enough for now. So let's jump into this. We are going to talk about the properties of this wave. Okay. So first thing, right? Remember that we labeled this section here as kind of like your resting position, okay, your starting point or whatever of your wave. Now, the wave itself is going to cause the particles of the medium or whatever it is to vibrate, to displace, right? And that displacement that you get away from the resting point is called the amplitude. I'm just going to label it with an A here, like this, and we're going to write A equals amplitude. Okay. Now, amplitude can actually be either the height to the top of the wave from the center or the depth from the center to the bottom of the wave, right? So amplitude is essentially how is the displacement basically, okay? That I don't know what that's supposed to be right there. It meant it to be an arrow like that. The displacement of particles relative to rest position. Now, some of you are saying, like, why isn't this wave height? Right. So if you've ever heard about like sailors or people who work in the marine industry or like out on the ocean or whatever, are talking about wave height. Wave height is actually from the bottom to the top of the wave, right? So that's different from what amplitude is, right? So, but we usually just talk about amplitude as though it were the wave height. So it's basically how far you're going to displace our moving object. So let's go back to our example here. So here you've got this wrench, and if we pull the wrench up and then back down again, right, the amplitude of the wave is, in fact, how the difference between this dotted line and the top of that wave, right? But if I do it like this, right, you've got amplitude up here and amplitude down here. See how those are two different amplitudes because they're two different pieces, right? Amplitude to here, amplitude to there. Okay. But in the ocean, if you're a mariner and you're on a ship and you're riding along, you're going to be like, oh, yeah, the wave's real tall because you can see into the bottom, you can see to the top. Okay. Speaking of waves and speaking of the bottom and the top, let's label those, shall we? The top of the wave is called the crest. The crest. And the bottom of the wave, right there, is called a trough or a trough if you are from not the United States. A lot of times people call it the trough, but you can call it the trough. That's fine. Okay. You might be familiar with troughs, like what, farm animals eat from, and crests as being like, the top. So there's a crest and a trough. Okay, so simple labels for you. All right, the rest of the stuff that we're going to talk about is kind of like how we talk about waves, less than how we label them. So you've got all the basic stuff labeled. Um, you can kind of see a couple of other quick things, and let's just start in some fresh space over here. I'm going to label a couple of points. So if we put a point here, where does the next time a particle is at exactly this point, right? So let's move through one full wave cycle. We started at the top, we go all the way down and all the way back up to where we started from, right? So one full cycle is what you see here. So that's one full wave cycle. We call that the wavelength. Okay. So the distance between one point that you put literally anywhere on a wave and that exact same point on the next wave is called a wavelength. So if you start here on this point, this is coming up, right? It doesn't go to this point right here. That's not right. Okay. Instead, it's actually going to go here, right? To the next symmetrical place where it's exactly the same. Wavelength can be from any one point on any one wave to that exact same positional point on another wave, right? Or on the next wave over, right? So you could do from trough to trough, you could do here to here, right? Do crest to crest, you can do any point to any point. That's a wavelength. Okay, here's our next thing. We label it with a capital T. Capital T for the period of time. Okay. So the period is actually how long it takes for each cycle. How long it takes for a cycle. Okay. Now, that cycle, AKA a period, right, is one full pass of a wave, right? So if you start here at the center point, right, and you end here at the center point, that's one full pass of a wave. So if it includes a crest and a trough, that is a period. Okay. So one period is one crest and one trough. So if we time how long it takes to create this whole thing, basically, we've got the period. Okay. So that's your period. This gets a little bit more confusing because there's another thing that we add to it, and we call that frequency. I want a color that we haven't used. And we're going to use F for frequency. I don't remember how to spell frequency. There we go. Frequency. And frequency is how many cycles, right, which we just talked about, how many periods, right, happen in some amount of time. So the easy way to think about this is if you're sitting on the pier and you're on vacation, right, wherever you are, you might be like, at a beach and you walk out on the pier so you can see the waves coming past you, right? You can look out at the side view of the waves and see them all going past. If you just count the number of crests in a certain amount of time, you're counting the frequency, right? How often are waves coming by, basically, right? So that's an easy way to think about it. How often are waves coming by? How many cycles are happening in some amount of time? Okay. Because if you count each crest, there has to be a trough between every crest. So you really only need to count one, right? Like one thing. You don't have to count crest, trough, crest, trough. You can just count crest, 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 crest. And me saying crest is the frequency. Okay. It's like how many waves per second, how many waves per minute, how many waves per hour, etc. Okay. So that's frequency. Now, what's interesting is that frequency and period are actually inverses of time or inverse of each other, right? So you can write that frequency equals 1 over period. You could also write that period equals 1 over frequency. They're the same thing. It's interchangeable, right? So if you have one, you have the other. Because period, right, is how many cycles or how long it takes for a cycle, right? How long does it take for the wave to happen? And then frequency is how many cycles, how many periods of this wave are happening in some amount of time, right? So if you have frequency or you have period, you have the other one because they're inverses of one another. Okay. So you might also know that if we're talking about frequency and we're referring to cycles per second, that's measured in hertz. So, you've ever heard somebody talking about hertz, maybe in music class, or maybe because you like music, or maybe, I don't know, mostly related to sound for me in my brain right now. We usually talk about hertz as the cycles per second. You might also have, I guess, motors can work in hertz as well, perhaps how many cycles per second. So, That's hertz, and that's how that works. Am I going to ask you to do problems that involve hertz? I don't think so. We're just trying to get the concept here. Okay. Let's see. There's one more thing. We talk about wavelength. Wavelength is actually a has a symbol that goes with it. That looks like that. Isn't that cool? Okay. So that's a lambda, and we're going to talk about what that means in a second. Okay. So we just found out that lambda is the symbol for wavelength, right? So I should probably put that down here. So let's add that to the list. Okay. I'm going to go ahead and write that lambda equals wavelength. And you can see that I labeled wavelength up there at the top, and it is essentially the length of the wave from one point to that same point on the next wave. So we don't really need to write length of the wave. We just really need to write distance. Distance from one point, any point on any wave, to that same point on the next wave over. Okay, that's wavelength. Now, why do we care about all this stuff? Let's talk about it. What's interesting is if we know the wavelength, we know how far the wave goes, right? And if we know the distance and we know the period, we know how long it takes for the wave to go, then we can calculate velocity, right? So let's use our brains here. Let's get some big brain stuff out. Okay. You guys know that velocity equals distance over time. And in this case, the velocity of a wave is equal to its distance, which is also the wavelength, right? Divided by how long it takes for the wave to cycle. And that is the period. I'm going to use a capital T because that's what you'll see, right? So wavelength divided by period, right, is equal to the wave's velocity. Now, we just talked about that wavelength, or sorry, that period T is the same thing as 1 over frequency, right? So if you have wavelength divided by T, you could also say that wavelength times F, wavelength divided by period, is equal to the same thing as wavelength times frequency, right? Because we know that frequency equals 1 over period, right? So it's the exact same thing. So if you know wavelength and you know either the period or the frequency, then you can calculate the velocity, okay? So I'm not going to be asking you to calculate specifically cycles per second by saying like there's this many cycles in this much time, how many hertz is that? I'm just going to either give you that or ask you to solve for frequency on its own, but only in these situations, right? So this is the stuff that we're going to be using to kind of do the math. Okay, is this particular information, right? So you're basically plugging in wavelength for distance and you're plugging in for time, either period or frequency. Okay, but you have to remember that they're inverses of one another. Okay, so this is how we're going to do it, and we're going to do some examples before I jump into it with you, or before you kick off on your own, rather.